Hi, my name is Dr. Kyle Montgomery. In this video, I'll be talking about a specific problem that I've given in the past on an exam where we're trying to find the Thevenin equivalent circuit for a given circuit configuration, as I've already indicated right here. So I encourage you to go ahead and copy this down in your notes as we prepare to kind of work through this. Now again, we remember that the Thevenin equivalent circuit is trying to help us simplify a circuit such as this where we have many different voltage sources as well as resistors here. We're trying to simplify it to a single DC voltage source and a single resistor. So the ultimate outcome that we want to get to is a circuit that looks like this, with again just the single resistor and the single DC source, where if these are terminals A and B, these would be the equivalent terminals A and B on this circuit, such that the voltage between these two terminals in either of these circuit configurations will be identical. It'll give us the same response from this side of the circuit, irrespective of whatever we might be attaching this circuit to on the other side. Okay, so the idea here is we need to first find, or in any order really, find the Thevenin equivalent voltage, VTH, as well as we need to figure out what this Thevenin equivalent resistance is, RTH, right here. So to begin, I'm going to go through the process of figuring out what the Thevenin equivalent voltage is. And to do that, we'll take a quick break, and I'll revise the circuit a little bit to go to that point. Because again, what we want to be able to find to determine this Thevenin equivalent voltage is what would be the voltage between terminals A and B in this open circuit configuration. Or in other words, as we know, if these are open circuit terminals, there's no current flowing through this resistor here and no current flowing through this resistor here. Therefore, the voltage we're really trying to find is specifically what's across this 10 ohm resistor right here. Okay, so now looking at the circuit where I've simply just removed the resistors that we had, because again, for finding the Thevenin equivalent voltage, those don't really play into what we're going to do. What we're trying to again find is the voltage across this 10 ohm resistor. Now note that I've defined the polarity of this Thevenin equivalent voltage as positive to minus. But again, as with many things with circuit analysis, it's really arbitrary how I define that. We will simply find that if the actual voltage across that 10 ohm resistor is positive to negative, then this quantity will be a positive quantity. However, if we do all the analysis and find that this is a negative quantity, then I could simply switch the polarity and then use that as a positive quantity. But regardless of how I do this, I just need to be sure that whatever polarity I define here is going to be the same as I define it in my equivalent circuit as is shown here. So now how do we go about figuring out what this voltage is across the 10 ohm resistor? Well, the most straightforward approach is to just use the well-known Kirchhoff's current law, or the KVL law, right? So here, if I just map out sort of a path entirely all the way around our circuit as such, this will give us a path through which we can add up, again, all the voltages around each of the given elements here, and then be able to figure out how we can solve to find specifically what VTH is here. So I'm going to start up here in this corner and just work our way around so we can write an equation to describe what we need to solve for. So here I have, again, a voltage drop I will indicate as a positive quantity. Any voltage rise will be a negative quantity. So therefore I have this positive 15 volts. Going across here, the voltage drop across this 10 ohm resistor, again, is the VTH that I'm looking for. So that's plus VTH. Coming around here, I come across this 30 volt source, and specifically now this is voltage rise, so this is going to be a negative quantity, so I'm going to say minus 30 volts. Coming across the voltage of this 5 ohm resistor, so I haven't defined what that voltage is specifically, but let's go ahead and define a given current that's flowing through this branch here, which I will indicate as I1. So therefore, we know through Ohm's law that the voltage drop across this 5 ohm resistor is going to be 5 ohms times I1. And we will indicate that this is indeed a voltage drop if we go plus to minus, because we're following the current there. So this will be plus 5 times I1. And that takes me back to the starting point, and we see we have no other voltage drops or sources here, and so we know that this equation has to sum to 0 to satisfy the KVL rule. So if we do some fairly simple math here to indicate what we have overall, we can see that we have, 15 minus 30 will give us minus 15 plus VTH plus 5 times I1 equals 0. So now we have a single equation, but again, now we have two unknowns. So what can we do to help us further satisfy or further get to the final answer that we want? Well, if we look at what VTH is, again, we've indicated some current flowing around this branch of the circuit. And so we know that the current flowing through this resistor has to be the same as through this resistor, except going in this direction, because again, these elements are in series. And so therefore, we could substitute for VTH as saying this is 10 times the current I1. And so if we substitute that in here, we have minus 15 plus 10 I1 plus 5 I1 equals 0. And so from there, we see that we can get 15 equals 15 I1, a little simplification, and therefore I1 is going to be equal to 1 ampere in this case. Okay, so then what we are ultimately looking for is not the current per se, but we need to get, again, this Thevenin equivalent voltage. And we know that, as we've already defined, that the Thevenin equivalent voltage is going to be equal to whatever I1 is times that 10 ohm resistor. So multiplying these two quantities, as we see, gives us 10 volts. And so this is now our Thevenin equivalent voltage, and so this would be the quantity indicated on this simplified circuit diagram. Thevenin equivalent circuit will be a 10-volt quantity. Okay, so now then the next step for defining our equivalent circuit is to figure out what this Thevenin equivalent resistance is. And so I'll set up the problem a little bit differently to figure out that, and we'll get going from there. Okay, so now I've redrawn the circuit in the original form, which we'll need to evaluate what the Thevenin equivalent resistance is. So now, again, a lot of students sometimes get confused in the fact that we've already done some analysis to find the Thevenin equivalent voltage, and for instance, we found what some current was traveling through this branch, and they sometimes want to use that to then figure out what the Thevenin equivalent resistance is. But again, we need to remember that these are really kind of separate problems that we're solving here. The Thevenin equivalent voltage is specifically figuring out what's the open circuit voltage between the terminals A and B, whereas the Thevenin equivalent resistance is saying, well, what is the equivalent resistance looking into the circuit from terminals A and B? And so in this case, the values of these resistors that we have here do, in fact, play a role in determining what that equivalent resistance is. So we really have to, again, look back at the original problem now for finding Thevenin equivalent resistance, and specifically look between these terminals A and B. So now there's a few different ways we could do this. The most simplified way, especially with working with DC sources, is to use the so-called like deactivation method. So remember that when we're deactivating a given source, we look at any voltage sources or current sources. Here we only have voltage sources. But if we have a voltage source, we put in a short circuit in place of that voltage source. And if we had a current source, we would put in an open circuit in the place of that current source. And after doing that, then we solve the problem of figuring out the equivalent resistance overall related to the Thevenin equivalent resistance. So very simply, we just take out these voltage sources here, okay, and put in a short circuit. Again, because these are voltage sources specifically. If we were dealing with current sources, we would do the opposite. We would actually leave it entirely open circuited. So now if we look at this circuit, looking in from terminals A and B, we can immediately kind of notice a few things, or a couple things rather. First, we notice that we have a short here across this 25 ohm resistor. So now again, remember that if I were sort of probing this circuit with some current, the current would always travel through this short circuit. It would never travel through this 25 ohm resistor because it always travels along the path of least resistance. So in essence, in order to find the equivalent resistance, this 25 ohm resistor plays no role in that outcome, as it were. So if we wanted to, just conceptually, we could actually just take this out entirely of the circuit, and that gives us even a simpler circuit such that we can figure out what the Thevenin equivalent resistance is. So now here we're just looking at a resistor network, and we can apply just our standard series and parallel rules. There's nothing very difficult about this specific configuration in order for us to do that. So again, say this is RTH looking into the circuit between terminals A and B. I see that I have this 5 ohm resistor in parallel with a 10 ohm. So I'm going to say RTH is going to be that 5 ohm in parallel with the 10 ohm combination. And then when I combine those two resistors here, then I see that I just have 3 resistors in series. And so what I'm going to add into this parallel combination of the 5 and 10 ohm resistor is this 23 1/3 ohm resistor and the 14 ohm resistor. So plus the 23 1/3 ohm plus my 14 ohm resistor as such, okay? So in order to work this out here, we know we can figure out the parallel combination of the 5 and 10, so that would be 5 times 10 over 5 plus 10, little shortcut rule that we've learned. Again, plus 23 and a third plus 14. Do a little simplification here. Now again, since this is a problem I've given on an exam, we know that we don't allow calculators in exams, so hopefully you'll get very quick at doing some basic math, even with fractions. And as such here, we know that we can get the solution of 25 ohms, okay? So again, this tells us now what this resistor value here, RTH, is going to be equal to 25 ohms. And now we've been able to define what the Thevenin equivalent circuit is as it related back to that original much more complicated circuit that we started with, okay? So again, a couple of key points here. When finding the Thevenin equivalent voltage and the Thevenin equivalent resistance, we sort of need to examine the problem under two different lights, as it were. So the Thevenin equivalent voltage, we asked ourselves what would be the open circuit voltage between the given terminals that we were looking at. And for the Thevenin equivalent voltage, or Thevenin equivalent resistance, we asked ourselves what would be the equivalent resistance looking into the circuit from those two nodes, and thus got to our solution of the 10 volt and the 25 ohm resistor. And also we need to pay attention to the polarity that we define here for that Thevenin equivalent voltage, but as I said when we were working through that part of the problem, that as long as I'm consistent with however I defined it when I asked myself what is that open circuit voltage originally to find this 10 volt answer, that's the polarity I chose for that source right there. So hopefully this gives you a little better perspective on how we can do that. Now that we have the Thevenin equivalent circuit, we can do several other things, such as ask ourselves what would be the maximum, the load resistor that we would need to deliver maximum power to some other side of the circuit as well, and various other things we could do. But this at least gives you a starting point for how we can work through and finding this more simplified circuit. Thank you.